So I'm going to start from where we left last time. So this was an important result which we discussed, small little theorem, that if we have a system, let's say a square system, for a square system, we are writing it as a matrix equation. So this system, let's call it 1, this matrix equation as 1, will have same solution set if I multiply this system on the left by some other matrix, so this one, number 1 and number 2, will have same solution set. I'm thinking of this guy now as a new system because I can multiply these two to get a new matrix and multiply this matrix with this vector to get a new vector. So 2 and 3 is just same thing. I've just multiplied 2. So these guys and number 1 will have same solution if and only if this matrix M is non-singular. So if you have, so what you have done, you have transformed your system. You have changed your system by multiplying with a matrix. And if that matrix is invertible, is non-singular, it has an inverse, then the two systems will have exactly same solution set. Or in other words, system 1 and 3 are equivalent. They're one and the same thing. We proved this last time, but let me quickly go through the proof again so that you recall. So I have to prove it two ways. I have to prove that if I have a solution, any solution of A, that's also a solution of 3. And then the reverse, because they're equivalent. Any solution of 3 is also a solution of A, 1. So suppose this x hat, I have got a list of numbers. This vector is any solution arbitrary. I'm not fixing it. Solution of 1. That means it satisfies. By definition, it means it satisfies the equation 1. Then all I have to do is multiply from the left by m. Multiplying by m from left. Let me change the look of this notebook. So I get m times a was n, and m times b was, I was calling it C, which implies that X hat, this guy, also satisfies three. So also because it was arbitrary solution, so that means all solutions of 1 are solutions of 3 as well. Now I can go the other way around. So suppose this y hat is a solution of 3. That means it satisfies this equation. This equation, open it up. This was just, this matrix N was just M times A, and C was just M times B. Now, because I assume that this M is invertible, I can multiply from the left by its inverse. On both sides. So multiplying by M inverse from left. And why? Because M is non-singular. So this just gives me identity. Similarly over here, and I get back AY hat is equal to B, which was my original equation. So this is saying that Y hat is also a solution of 1. So all solutions of 1 are solutions of 3, and all solutions of 3 are solutions of 1. So system 1 and 3 are equivalent. So this gives us this important idea, which is just the same idea which we have been discussing before, just expressed in a new form, that we can transform our system to a simpler form perhaps, I should say perhaps we can. Into simpler form by multiplying with some non-singular matrix. So you start with some system which is written in terms of some matrix A of coefficients, and you can look for some matrices which are non-singular and multiply those matrices with the system so that A turns into some N, like over here, like here. And you're hoping that N has a simpler form which is easier to solve. So you can shop around for many M. As long as they are non-singular, it's fine. You can multiply with them. And the new system you get, you are guaranteed that it has same solution. So you are solving the same system. This is what we have been doing when we were doing row operations. We had one matrix available, matrix of coefficient, we were transforming it. And we were saying when we transform it into another matrix, it's still the same because we were transforming it through row operations. This time, we're going to transform it by multiplying with some matrices. So let's see how that happens. The idea is that we will still be doing row operations, but we will be implementing through multiplying with some matrices. So this is the main idea. Implement, because we know that row operations, how do they work and how we can simplify a matrix using row operations. But this time we will implement row operations through multiplying with some matrices. And when we do that, we have to take care that the matrices with which we multiply must be non-singular, because we have no guarantee that if we multiply with a singular matrix that we remain in the same system. The solutions may change. We have no theorem for that. So this process, so these matrices which accomplish these row operations, these are called elementary matrices. And let's see what's going on over here. Okay, so let's see what form they take. Uh, Before I kind of we try to guess what form they take. So for example, what I'm trying to achieve. I have three main row operations and I'm gonna have matrices for all of them. So for example, you have this matrix. And I want to exchange row 1 and 2 in this matrix. And I want to do it by, I'm doing it only for square matrices. I have a 3 by 3 matrix and I want 3 by 3 back. So I multiply it with the 3 by 3 matrix. And I have to guess a matrix, whatever that is, so that in the answer of the matrix multiplication, I get these rows exchanged. This is what I get back. So it may seem like it's how are we going to do it? And for all kinds of matrices, all sizes, exchanging row 1 and 2 was the problem over here, but we will need to exchange row 1 and 4, 4 and 2. So how are we going to guess all those matrices? Well, one method of matrix multiplication, which we discussed last time, is going to come very handy. So let me remind you. So that was matrix multiplication through row into row, using rows in both the matrices. So what was that? That if you have these matrices, you have a matrix over here, and multiplying with another matrix. You think of both of them as composed of rows. And what's the idea of multiplying by using rows in both matrices? You start with this first row and you make linear combinations of the second matrix, of the rows of the second matrix, using the numbers in the first row, and that gives you the first row over here. So to construct this row, you multiply this with this, this goes with this row, so you make a linear combination, and this goes over here. You make this linear combination, and that gives you the first row. Then you pick the second row over here and start making linear combinations of all these rows using these numbers, and that gives you the second row. Again, pick the third row over here and use these numbers to make linear combinations of the rows of the second, and that gives you the next row. So if I use this idea and take this matrix, then it's very easy to guess. Because if I write, can you please turn off your mic? First of all, let's start with this thing. That when I multiply this matrix with identity, why do I get this matrix back? So thinking in terms of these rows, I am multiplying this number 1 with the first row, multiplying this number with the second row, this 0 with the third row to get my first row back. So since I'm only multiplying in this row, the first row with a 1, so I get the first row back. So make a linear combination of these rows. When you do that, since only this guy was non-zero, so you get the first row back. Now you have to construct the second row. You again making the linear combination of these rows. Since you have only put the 1 in the second place, you get the second row back. Similarly, the third one. These two are multiplied by 0. Only the third place has a 1, so you get the third row back. So that kind of immediately tells you that if you want to exchange the first and second row, for example, what you need to do. You're going to make a linear combination. So you want the first row to be multiplied by 0 and second with 1 and third with 0. This will give you this row back over here. Now in the second row you want to put this back. So you make a linear combination. So in the linear combination you want to multiply this first row by 1, second by 0 and third by 0. So you get this back. And since you did not touch the last one, that stays same. So this matrix over here this will achieve for you exchange of the first and second row. And it's called an elementary matrix, and this matrix, people give them different name. I'm just going to call it the elementary matrix of the first type. First type because it achieves the first row operation of exchange of rows. And I can put another label that is exchanging row 1 and 2. Now you can tell me what matrix is going to exchange rows 1 and 3. So I want to, in my first row, I want the first and second row to be gone and pick the third row. Second row is not changed, so I just put this back from identity. And in the third row, I want to put the first row. So I start with a 1 and put zeros. So this guy would be, I can call it 1, 3. And if I want to write, for example, 2, 3, so first row I'm not touching. In the second, I have to pick the third line. And in the third, I have to pick the second line. And you can extend it to any size. And you can see what's happening over here. Any ij exchange, if I want, this is just identity matrix. Take the identity matrix and exchange rows I and j in the identity matrix. You can look over here. So this is the identity. I exchange row 1 and 2, I get this. This is the identity. I exchange row 1 and 3, I get this. Exchange row 2 and 3, I get this. You can do it in any size. Because as I had explained over here, identity matrix picks up the rows in this method of multiplying, picks up the rows one by one to give you back the matrix. So if you exchange 2 rows, so it's going to just exchange the order of picking of those rows. So very easy to guess that how you exchange rows. You just take the identity matrix, and in the identity matrix exchange the rows. That gives you the elementary matrix, which achieves for you the job of exchanging the rows. Then, so our goal typically is what we want to do when we are given a matrix and we want to solve a system. We want to bring it to row echelon form. Well, even better, bringing it to reduced row echelon form. So to do that, we needed 3 operations. Sometimes we had to multiply with a number as well. So how can I multiply with a number? So for example, if I want to take this 2 and make it 1, I want to bring a 1 over here. What can I do? This is an easy one. I want to multiply the first row by a number. And I know that when I multiply, I make linear combination. So in the linear combination, for the first row, the number for the first row, I can just pick the number with which I want to multiply. So I can put, so suppose I want to multiply this by a half. I can put a half here. So then the first row which I will get back will be half times this, and the others are 0. So I will get this back. Similarly, if I want to do, if I suppose I want to multiply the third row by a 2. So I start with the identity, don't do anything to the upper rows because they produce these rows back. The third row is gonna pick for me the third row, but in that picking, I just multiply, I want to multiply this row by, let's say, a 3. So I just put a 3 here. It's gonna give me this back. So these matrices, I can call them elementary matrices of type 2. They multiply one row by a specific number. So something like that. You're multiplying with 3, row 3. And over here, you're multiplying row 1, you're multiplying with half, row 1. So again, it's very simple. If you want to multiply a row by a number using a matrix multiplication, take the identity matrix and whatever row you want to multiply with a number with, multiply that number to your identity in your identity matrix, and that will give you the elementary matrix which achieves that job. Then the last operation is, which we are interested, is adding one row, multiplying a row with a number and adding it to some other row. So for example, if I want to add -1 times this row, second row to the third row, how can I do that using the matrix? First of all, the matrix with which you will multiply, you again start with the identity. And those rows which are not going to change are not going to change in your identity matrix, because the identity matrix rows pick up the rows for you. So this row picks up the first row, that's not going to change, so I leave it like that. I'm adding second row to the third, but that doesn't change the second row itself, so I leave it like that. Now I want the second row to be added to the third row. So in the identity matrix, this guy picks up the third row, and this place picks up in the linear combination the second row and adds it to the third row. So I can multiply, I just have to put a 2 here. Well, I wanted to multiply it with a -1. So I just put a -1 here. And that should achieve for me this back, but this row achieves for me, leaves this as 0, multiplies this with -1 and adds it to this. So what's the rule? If you want to, this is the elementary matrix of type elementary matrix of third type. If you want to multiply with some number alpha, rho I, well, let me write it like this. Alpha times rho I and add it to rho j. What you need to do in your identity matrix, it's a very easy pattern. In your identity matrix, take the ith row, multiply it with alpha and add it to the jth row. Add alpha times ith row in identity matrix to jth row, which also means that in the jth row, in ith column of jth row, where you were expecting a 0, because in the identity matrix only the jth column of the jth row will be filled with a 1. So in the ith column of jth row, put an alpha, and that should do the job for you. So any questions so far? So I can construct any of these matrices, and multiplying with any one of them will perform a row operation for me. I can keep performing these row operations. So if I start with a matrix A, and I have a sequence of row operations which takes it to some other matrix B. And since these are row operations, I know that these are equivalent. So this sequence of row operations I can achieve by a sequence of these elementary matrices. So there will be a bunch of row operations, and they can be achieved by multiplying by these elementary matrices one by one. So the first one does the first row operation, the second one does the second, and the third, and so on, until finally I'll get my matrix B. And if I want, I can multiply all of these together to get one big matrix. That won't be like a single elementary matrix. It would be just a product of these elementary matrices. But I can see it as one matrix, multiplying A to give me B. So if B, for example, for me is a reduced echelon form, I'm trying to go to the reduced echelon form from A to a reduced echelon form of A. Well, let me call it, to avoid confusion, let me give a name, A reduced echelon. So it's telling me that I can do it. I should be able to do it. I must be able to do it, because I know that row operations can take me to the reduced echelon form always. And row operations can be achieved through elementary matrices. So finally, I will have one matrix which, when multiplied with A, will give me the reduced echelon form of A. This is the reduced echelon form. And these are products of elementary matrices. Now, the first result which we discussed today, that comes into play because of a property of these elementary matrices. So that property is all the elementary matrices are non-singular. They have an inverse. How can I see it and how do I find it? It's very easy. So suppose if I consider the elementary matrix of type 1, which exchanges row I with J in the matrix A, then I again multiply with the same matrix. I again exchange row I and J. So what's going to happen? Finally, I have not exchanged anything. So this is equal to A. This means that this is identity. I didn't do anything to my matrix. Can you please turn off your mic? That means these elementary matrices of type 1, they are inverses of each other. They are inverses of themselves. Take any elementary matrix, it's an inverse of itself. So let's take this guy. कौन सा लें? Which one you like? Let's take this one. E112. First and second row exchange किया मैंने in the identity matrix. So that gives me an elementary matrix which achieves exchange of row 1 and 2. But you can check that it's an inverse of itself. So ये क्या आ रहा है 0 1 1 0 0 0 0 0 0 0 0 0. When this goes, this is dotted with this, you get a 1 0 0 0 0 1. So it does give us back the identity. So we have proved that the identity matrix of type 1, which achieve the row exchange, they are invertible, and the inverse is just themselves. Now the identity matrix of type 2, where you multiply with alpha some row I, they are of this form. Let's say I've just written a very, very big matrix. So ith row mein, you multiply with some alpha. Well, probably would be better if I pick a example. Let's write this. Uh, 2 times the second row. So this elementary matrix is this, multiplies the second row with 2, Instead of 2, let me take an arbitrary number. Multiplies the second row with alpha. Now, its inverse is very easy to guess.
1 upon alpha.
Yeah. If I just put this guy, because this is the same elementary matrix. What is this guy? This is the elementary matrix of type 2, which multiplies the second row by 1 over alpha. So it's going to multiply the second row of this guy with 1 over alpha. And that's going to give me back 1.
So third row, third element should be 1.
Third row, yeah. I multiplied it from the right, but because I know the inverses work both ways. But the correct way to think about it is this. That this guy itself is an elementary matrix which multiplies the matrix which comes to the right of it by 1 over alpha. Its second row by 1 over alpha. So when I'll multiply the second row of this guy with 1 over alpha, I'll get the identity back. So in a similar way, if you have any elementary matrix of type 2 with ith row having an alpha over there, you can eliminate that alpha by multiplying it with a elementary matrix whose ith row has 1 over alpha. So all of these guys also have inverse, and the inverses are very easy to find. Now for the third type, so suppose you multiply the second row with alpha and add it to the third row. So we know what we need to do. Multiply the second row with alpha and add it to third row. That's the elementary matrix. Now if I want to bring it down to identity, this matrix, I have to remove this alpha. How can I remove it? By multiplying the second row with minus alpha and adding to it. Right? Because now this is also an elementary matrix which adds minus alpha times the second row to the third row. And when we do that to this guy, I get a 0 back over here. And you can also think in this term like this guy achieves whatever comes on the right, adds the alpha times the second row to the third row. So if I just subtract that, I will get the original matrix back. So that must be this guy. So this is the inverse of this guy. And they are inverses of each other, all of these guys. So all elementary matrices have inverses. Matrices have inverses which are elementary themselves. So this has consequence. The consequence is that if I start with a matrix A, if I have, let's me write an equation. If I have an equation like this, and I bring it, I multiply it with a bunch of elementary matrices on both sides. So this guy, I'm changing to the reduced echelon form. And whatever I get over here, I get. Since all of these guys were inverses, are invertible, the product is also invertible. We proved it last time. The product is also invertible. So this equation I can write as some big E multiply A and that same big E multiplying B, and we just proved the theorem that if this is invertible, then these two guys have same solutions. Which we kind of already know. So I can put into reduced echelon form using these elementary matrices, and I am guaranteed that the solution would be same. I don't even have to go to reduced echelon form. I can just stop in between. I can do whatever I want, any operation I like. As long as I multiply with a bunch of elementary matrices, the two equations which result, the original and the one which results, are going to have same solutions. This has a very interesting application. So far in practice, this is just a helpful way of thinking, and it will help us in proving different properties of solutions, thinking about them again. But in the end, all I'm doing is row operations. So we haven't really learned a new way. Well, whatever new way you think of, you can boil it down to the elementary row operations in the end. Everything is built upon that concept. But this way of thinking has an interesting application. So what's the application? Uh, let me okay, let's recall. What's the recollection that if a system has unique solutions, if a square system has a unique solution, then the reduced echelon form of it is identity. You've kind of seen it, but let's see it again. So if a square system has a unique solution, so it has, let's say, n variables. And if it has unique solution, that means it has no free variable. because unique. If it has no free variable, how many lead variables it has? Each variable is lead. So in the echelon form, we know we can always put in echelon form. Its matrix, echelon form matrix will look like this. So it has a lead variable. In the second row also, the second column will have a lead variable. In the third row, the third column will have a lead variable, and so on. If I write 4 by 4, it will look like this. Because of the very property that there are no free variables. Free variable would mean that I'll start with some 0 in some row with an extra 0. So when I go to the reduced echelon form, I start subtracting upwards. And since I don't have a 0, extra 0 in any row, I will be able to eliminate all the zeros up over here, all the zeros up over here, and all the zeros up over there. I will not get a completely 0 row. So the reduced echelon form since in each row, in the ith row, the lead variable appears and at the ith place, and in the reduced echelon form, I eliminate everything above and below the lead variable. The reduced echelon form is exactly identity. Zeros everywhere else. So what does this mean? This means if I have an equation like this, and by doing multiplying with these elementary matrices, I am trying to convert it into the reduced echelon form. I do that. This multiplication gives me the reduced echelon form. Now, if the solution is unique, then I know that this guy is identity. So what does that mean? This means that E times A is identity. So this means that this E, product of all these elementary matrices, the E is just inverse of A, right? So when I'll try to put this A into reduced echelon form, my reduced echelon form will turn out to be the identity. And because of that, this product is just telling me that this is the sequence of elementary matrices constructs for me the inverse of A. So sequence of elementary matrices that puts A into its reduced echelon form is actually A inverse. So then that means this guy En, E3, E2, E1 is A inverse. I can just add an identity on both sides. That doesn't do anything. And keep it written like that on the right hand side. Now if you think of this equation, what is it doing? It's performing the row operations on identity. The same row operations which you performed on A to get the identity. If you perform the same row operations on identity, you will get the inverse of A in the same sequence. So is that clear? This equation is saying that take the same sequence of row operations which put your original matrix into the reduced echelon form or into an identity. If the same sequence is applied on the identity, you will get the A inverse. So this gives you a method of computing the inverses of matrices. Computing the inverse of matrix using Gauss-Jordan method. Because these elementary operations, I can think of them as being done through these matrices, but I don't have to actually practically physically do them using these matrices. I know because they implement the row operations, I can just work with the row operations directly. So this is a very clever way. So suppose I want to find the inverse of this matrix. 2, 1, 0 and -1, 0, 1. What I'll do, I'll write an identity on this side. And then I start doing row operations, looking at the on the left hand on the green matrix, and try to put it into its reduced echelon form, or in other words, I'm trying to put it into identity using row operations. But I'll keep doing the same row operations to the blue matrix on the right hand side as well. And by the time I'll get an identity on the left, I would have the inverse of this matrix on the right. So let's just do this example. What can I do? So for example, I want a pivot here. I can start by exchanging row 1 and 3. Row 1 and 3. Second row remains same. Now I can add, I'll make this one later, but I can add 2 times this to row 2 and 3 times the row 1 to row 3. So the first row doesn't change. And 2 times this added to this. Now 3 times row 1 added to row 3. Plus 1. That's what I get. Now I can multiply the row 1 by minus 1 because I'm moving towards making it an identity. They remain same. Now I have got my echelon form and I just have to make it reduce. So I have to eliminate the numbers above the lead variables. So all I have to do is minus 2 times row 3 added to 2 and row 3 added to 1, row 1. So the row 3 remains same. And when I do minus 2 times to this, I get a 0. Minus 2 added above gives me a minus 2, 1. Minus 6 plus 2 gives me a minus 4 here. Now I'm just adding these rows. 1, 0, 0. So I've got the identity. That means in this step, I should have the inverse on the other side. 1, 0, 2.
Sir, could you repeat how you got 0 for row 1, column 3?
Huh?
Could you repeat how you eliminated minus 1, row 1, column 3?
This guy?
Yes, sir.
Yeah, so I just added row 3 to row 1. So once you are in echelon form, you know that these guys are not gonna change, which are on the left of this lead variable. So I just add this above, and that will make it 0. So the claim is that if this was our starting matrix was A, let's call it A, this part, then this part is A inverse. So A inverse is 1, 0, 2, minus 2, 1, minus 4, 1, 0, 3. And let us check if it's really inverse. 3, 0, minus 2, 2, 1, 0. 3, 0, minus 2, 2, 1, 0. And I had a minus 1, 0, and 1. So when I can multiply with the dot product. So when I do that, I have 1 times 3, 0 times 2, 0, 2 times minus 1. So I have 3 minus 2, a 1. In the second place, I have this row dotted with this. So 0, 0, 0. The third, I have minus 2, plus 0, plus 2. Similarly, over here, I have a 6, 6 plus 2 plus 4. So a 0, then a 0, 1, 1, 0, 1, 0, 1. Then I have a plus 4 plus 0 minus 4, a 0. Then 3 plus 0 minus 3. So a magic is happening. 0 and minus 2 plus 3. So checks. This is the inverse. So that's the first method of finding inverse. That's the most standard, and that's like our starting way of how to construct an inverse. Again, it's equivalent to solving a system of linear equations because it's based on row operations. Let's try another example that will reveal something. I may have to go like 2-3 minutes above. So I have this matrix. And I want to construct its inverse. So I write the identity on this side. And start using row operations to make this identity, and this guy will be converted into inverse. So the first step I can exchange row 1 and 3 to make a nice pivot over here. So when I do that, I get this. Second row is not changed. And the first row comes at the third. Now I can start making these zeros. So -1 times the first row is now gonna stay same. And -1 times first row added to the second gives me a 0, a -1, a -1, 0, 1, and this guy was actually so I get this was 1, so -1 into 0, -1. And over here I get a 0, -3 plus 1, 2, and this remains a 2 because there's a 0 above. This remains 1, this remains 0, and I get a -3 plus 0 gives me a -3.
Where did you multiply row 1 by 3 and then add that, -3 and then add that to row 3?
Can you speak again?
Did you multiply the first row by -3 and then add that to row 3?
Yeah, multiply the first row by -3 and added it to the third row.
Thank you, sir.
Oh, so yeah, so there is some mistake over here. -3 plus 1 should give me -2. Now let's see if I have done any mistake. No, so things are fine now. And now I can multiply. Well, I didn't achieve what I wanted to because I wanted to show you a failure. But I made a mistake in my notes. I thought that there's a 2 here, but there's a -2. So this will be a nice matrix. It won't fail. So we just got another example, nothing more. Now I can multiply by 2 and add below. I get 0. 2 plus 2, 4. 1, 2, minus 2, minus 3, minus 1. And now all I have to do is make it 1.
Sir, -5 नहीं होगा, -2, -3.
Minus 2, minus किसकी बात?
लास्ट एंड में लास्ट कॉलम में जो आपने
इधर?
बिल्कुल लास्ट नंबर रखा है
ये तो ये minus
Yes.
2 था. Yeah, minus 2, minus 3, minus 5. So now I make it a 1. So I divide by 4. Now only one step is needed. I have to make, well, 2 steps. Make minus times this added above and minus times this added above. So let me do it in one step. So second row is being added above with a minus. So -1, 2, and this row is being added over here. I get a 0, minus 1 by 4, minus half and half, a half, plus 5, 1/4, and I'm subtracting 4, 4/4. So I got left with a 1/4.
Sir, can you
ये वाला स्टेप समझ में नहीं आया.
कौन सा समझ में नहीं आया?
echelon form?
How did you get row 1 column 2 to be 0?
So I यहाँ तक तो ठीक है ना? Now
हाँ जी सर.
I want to make every one of these guys इनके ऊपर भी 0 लाना चाह रहा हूँ. I want to make it identity. So I multiply this with -1 and add it above.
But sir, -1 -0 भी तो -1 हो जाएगा ना for row 1 column 3.
Row 1 column 3. Oh yes. Yeah. So what I should have done? So I did a mistake. What I should be doing first is starting from here. First
Okay.
add this above because that doesn't bothers anything over here.
Change
So
that, of course.
that's the method to do it. Start from the very right when you are eliminating above. When you are eliminating
Okay.
below, start from the left, and when you are eliminating above, start from the right. Yeah. So first I had to do that. So there is mistake. So just complete it. First add this over here, and then add this over here. So I did this first, which was the mistake. Anyway, so when you complete it, you get a matrix over here, and that is supposed to be the inverse of A. So let's stop here. Again, a little bit slow than I expected, but we're doing not too bad. We have missed one lecture, so in like about 3 weeks, we are just about to finish the first chapter. It's not too bad. We have to increase the speed slightly, but I think we are doing not too bad. So you have got the homework, right?
Yes, sir.
Okay. So now I'll see you for the tutorial on Saturday. Bye-bye.
Okay, sir. Thank you.